Welcome back to Hansen Theory. So far, you have built a strong theoretical foundation. Now we move into the most important phase, real industrial application. This is where Hansen Theory stops being academic knowledge and becomes a daily engineering decision tool. Let's start with a common automotive coatings problem. An OEM clearcoat shows haze formation after humidity exposure. Initial lab tests show acceptable curing and gloss, but field performance fails. Traditional troubleshooting focuses on curing temperature or resin grade. Minority thinking engineers look at molecular interaction mismatch. By mapping resin, cross-linker, solvent blend, and additives in Hansen Space, engineers observe that humidity shifts hydrogen bonding dominance. This increases effective RA distance between polymer network and absorbed moisture. Local incompatibility zones form inside the coating. Microphase separation occurs. Light scattering increases. Haze appears. Solution: adjust cosolvent ratio and additive selection to stabilize hydrogen bonding distribution. Red is reduced under humid conditions. The coating remains optically stable. Next, industrial anti-corrosion coating failure. A protective epoxy coating shows premature delamination on steel structures. Adhesion tests pass initially. Field exposure causes coating liftoff. Hansen modeling reveals poor interaction compatibility between epoxy resin and surface pretreatment layer. RA distance between substrate chemistry and resin polarity is too large. Hydrogen bonding potential is underutilized. Engineers modify primer formulation using polar coupling additives and solvent blend adjustments. Interaction alignment improves. Interfacial bonding strength increases. Delamination stops. Now consider pigment flocculation in decorative paints. A high chroma color shows shade drift after storage. Viscosity slowly increases. Settling becomes visible. Standard approach: increase dispersant dosage. This often worsens stability. Hansen analysis reveals pigment surface polarity mismatch with polymer binder. Current dispersant bridges are insufficient. Red remains near instability threshold. By selecting a dispersant with better hydrogen bonding alignment and adjusting solvent polarity slightly, RA distance drops. Pigment particles remain separated. Storage stability improves. Color consistency returns. Next case: high solids industrial coating with application defects. A high solids coating meets VOC regulations but produces orange peel texture after spraying. Flow additives are added repeatedly with limited improvement. Hansen mapping shows polymer-solvent interaction imbalance at high concentration. Viscosity rises too rapidly during solvent evaporation. Surface tension gradients form. Engineers redesign solvent blend using Hansen-weighted coordinates to stabilize molecular mobility window. Evaporation profile becomes smoother. Flow improves. Surface leveling increases. Now consider waterborne coating foam problems. Excessive foam forms during mixing and application. Defoamer dosage is increased. Cratering appears. Hansen analysis identifies that defoamer compatibility is too high. Instead of destabilizing foam interfaces, it dissolves into bulk phase. Engineers select defoamer with controlled incompatibility. Local interaction imbalance is introduced at air-liquid interface. Foam collapses efficiently without surface defects. Next case: curing inhibition in two-component systems. A polyurethane coating shows incomplete cross-linking. Hardness remains low. Chemical resistance fails. Hansen evaluation reveals additive interference at reactive site interfaces. Certain surfactants block functional group accessibility. Engineers replace additive system with lower hydrogen bonding interference profile. Effective RA between reactive groups decreases. Curing efficiency improves. Mechanical performance returns. Now consider scale-up problems. A formulation works perfectly in lab. Production batches show instability. Hansen modeling combined with shear and temperature data shows that processing alters effective interaction environment. Additive distribution changes. Local red increases. Engineers redesign formulation robustness using interaction margin buffers. System remains stable across processing variations. Now, What separates average engineers from minority thinkers? Average engineers react to symptoms. Minority thinkers predict behavior before failure happens. They use Hansen Theory to model interaction balance before formulation testing, predict compatibility limits, design solvent blends strategically, optimize additive synergy, anticipate environmental sensitivity, reduce trial and error cycles. This saves time, cost, and material waste. It improves performance consistency. It strengthens formulation confidence. Most importantly, it transforms formulation from empirical art into molecular engineering discipline. Industrial success does not come from copying formulations. It comes from understanding interaction logic. That logic is Hansen Theory. In the next episode, we will bring everything together with scaling lab formulations to production reality, showing how to translate molecular design into factory-level performance control. If you want to solve real coding problems with predictive engineering instead of firefighting, continue this masterclass. This is Hansen Theory.